Calculate each of the following. Explicitly show any relevant substitution or algebraic or trigonometric manipulation. In the case of a definite integral, give an exact value and not a numerical approximation. Part A, integral e to the 3x over 1 plus e to the 3x dx. Okay, so my thoughts on this one, I've got a numerator and a denominator, and the more complicated one is the denominator. And so my first impression is maybe I can let u equal this entire denominator before we go through the details. In our heads, if we let u equal the entire denominator, and the derivative of 1 plus, that's nothing, and the derivative of e to the 3x is e to the 3x times 3, and my goodness, there's an e to the 3x sitting there, so the times 3 is the only issue, the only thing missing. So this feels like a very promising u substitution. Let's try it. So we let u equal the whole bottom, take our derivative, don't forget the chain rule, times 3. Also don't forget the dx, we're putting it on the right-hand side here. Then we're going to solve that equation right there for dx. So du over 3e to the 3x. Now I'm ready to do my substituting. So the original integral is equal to, I've got the e to the 3x on the top. The bottom has all been replaced by u, and then the dx is now being replaced by this last thing I wrote there on the left, du over 3e to the 3x. And then good things happen because the good things would happen if I copied it, right? E to the 3x up there. So good things happen because the e to the 3x is canceled. And so we're left with the much simpler integral of du over 3u. And that is equal to 1/3 can come outside, that's the 3 on the bottom. Du over u, that's easy, that's ln. So we go ln of u, don't forget the plus c. And then the last step is to go back, change the u back to the x's. So ln of 1 plus e to the 3x plus c. So there's our answer. Technically, ln should have absolute value inside. I'm not worried about that detail. Okay, part B. Integral cosine of x over the square root of 2 minus sine of x dx. Again, my first impression, I see a fraction where the bottom is much more complicated, so maybe I can let u equal the entire denominator. And if I do that, if I let u equal the square root, then we're going to have to change that to 2 minus sine x all in parentheses to the 1/2 power. And if I take that derivative, it's quite complicated. It's a 1/2, 2 minus sine x in parentheses to the negative 1/2, and then finally times the derivative of the inside, the 2 minus sine x. I'm just going to stop there. That is not promising because that is far more complicated than what we have to work with on the top. So the first attempt was similar to up here, let u equal the whole denominator, and it's just not going to go anywhere. So we don't need to spin our wheels on that one. But I see a square root, and sometimes letting u equal the thing inside the square root works. So if we let u equal just the stuff inside, the derivative of 2 is nothing. Derivative of negative sine x is positive cosine x. Oh my goodness. Wait, I think I said that wrong. Negative sine x is negative cosine x. Either way, we've got a cosine x sitting right there. That is just fantastic. So this is promising. We're going to let u equal not the whole denominator, but just the stuff inside that radical. 2 minus sine x. Derivative is negative cosine x. Don't forget the dx, that's important. Solve this for dx just like we did up above in green. Du over negative cosine x. Integral equals, all right, copying the cosine of x, copying the square root because we didn't deal with that yet, but now the 2 minus sine x becomes just plain old u. And then instead of times dx, we're going to put what we solved for, du over negative cosine x. And good things happen. Cosine x cancels with negative cosine x, so that's just a negative 1 down there at the bottom. And so the new integral, du upstairs, negative square root of u downstairs. Okay, this looks much better than the original integral, but there's still work to do, so let's make sure we can finish it. Negative can come outside, I'll put it on the top. Doesn't matter whether it's on the top or the bottom. That square root of u for sure is going to get changed to u to a power. It's u to the 1/2, but that's on the bottom. Let's do one more step in our heads and bring it up to the top. And at the end of the day, it's a u to the negative 1/2 when you bring it upstairs. And that is something I can integrate. It is u to a power. Those are easy. Negative. Okay, u to the, add 1 to the power, divide by the new power, plus c. And then the last step here is just going to be to change the u back into the x's. Okay, negative, dividing by 1/2 is the same as multiplying by 2. I'll put that. And then the x's were 2 minus sine x. I do not have enough room here. Let's try this again. Okay, so we said 2 minus sine x, and that is to the positive 1/2 power, and then plus c. Okay, part C, integral x e to the 3x squared plus 4. I see the product of two things. I start thinking, maybe one of them is u and the other one is du. If we try letting u equal this entire thing, the derivative of e to the 3x squared plus 4 is e to the 3x squared plus 4 times 6x from the derivative up there. But I don't have any of that here. I don't have anything near as complicated as another copy of e to the 3x squared plus 4. I just have x. So that's not a good choice. But sometimes when you have an e, you let u equal just the power on the e. And in this case, the derivative of 3x squared plus 4 is 6x, which looks an awful lot like what I have. That looks promising. Let's go with that one. Okay, so we're going to let u equal just the power, 3x squared plus 4. And therefore du is 6x. Don't forget the dx. And then we will solve this equation for dx by dividing both sides by 6x. And then the original integral is equal to integral. Copying the x, copying the e, the 3x squared plus 4, that's our u. And then instead of dx, what we just solved for, du over 6x. Good things happen. X's cancel. And we get an integral we can handle. Okay, that over 6 can come outside as a 1/6. Then the integral of e to the u du is just e to the u plus c. Last step is to change it back to x's e to the 3x squared plus 4 plus c. Part D, integral x e to the 3x plus 4. This one looks very similar to part C. It actually looks simpler than part C because here it was squared and here it's just to the first power. Okay, letting u equal e to the 3x plus 4, that's not going to work for the same reason it didn't work in part C. Letting u equal 3x plus 4 gives me a derivative of just plain 3. That's a problem. It's not complicated enough. I've got an x out here that needs to cancel with something, and it isn't going to happen with the derivative there. So unfortunately, my two natural choices for u substitution didn't work. We need a more powerful technique, not powerful, but a more complicated technique here, and that is integration by parts. And I'm thinking that because I've got a polynomial x multiplied by e to some stuff. And polynomials times e, oftentimes e to some stuff yield to integration by parts. So let's give that a shot. Okay, here we go. U equals dv equals du and v. Sometimes you got options here, but there's only one correct choice. You need to put something in the u slot that gets better when you take a derivative. That is x. X becomes simpler when you take a derivative. It just becomes 1 dx. Everything else goes in the dv. That's e to the 3x plus 4 and the dx. And then we need to do an integral, an antiderivative of that to get our hands on v. So what's the antiderivative of e to the 3x plus 4? Well, that is actually a full-fledged u substitution. I'm going to write it here, and then I'm going to erase it. But the integral of e to the 3x plus 4 dx, you can pause the video here, do the full-out u substitution, and then come back when you've got it. But I just don't have the room to write it on this page. So I will say, after you do the u substitution there, letting u equal to 3x plus 4, you are going to get e to the 3x plus 4 Actually, I'm going to put a 1/3 in the front. 1/3 e to the 3x plus 4. And then there's a plus c, but we don't write that in the integration by parts formula here, not at this stage. So we'll just make that note there that this step here is a full-on u sub without the details written here. Okay, so now I'm ready to do my integration by parts formula. Original integral equals, so remember it's u times v, that diagonal, x times 1/3 e to the 3x plus 4, minus, always minus, integral of v times du. So that's the bottom row multiplied. So 1/3 e to the 3x plus 4 times du, that's just dx. Okay, equals, okay, I'll just write the 1/3 first here. Minus, okay, now that 1/3 is going to come out, and I'm going to be left with the integral of 3x plus 4 dx. But hey, that is exactly the integral that I said you need a u substitution for, and the answer for that integral, not including the 1/3, but just the integral of this piece, is exactly what we did here. So it's going to be another 1/3 e to the 3x plus 4. So hopefully that's not too many words. We're just going to write this first 1/3 is the 1/3 that was already there. This next 1/3 is coming from the u substitution. I'll put it in parentheses, try to highlight it and make it look different. And then plus c at the end there. In fact, why don't I actually highlight it? So this thing here, oh goodness. So this thing here got copied. Where did it get copied? Right there. Okay, and then just one last step is to smush together those 1/3 at the end. So we'll call it 1/9, and then I think this one is done. Integral from negative pi over 4 to pi over 4 of tan squared x dx. Okay, tan squared x, that does not look like one of our elementary integrals. You could try u substitution, letting u equal the whole thing, but the derivative of tan squared x, thinking of it as tangent of x in parentheses squared. Derivative of that thing is 2 times tangent x times secant squared of x, which looks nothing like what we have. We don't have anything left to play with if we let u equal the whole thing, so that doesn't look good. You could maybe think of letting u equal one of these tangent x's, and then the derivative of that du would be secant squared x, which doesn't look like what we'd have left. So neither of those is promising. So the technique here is actually to use a trig identity first. It's not a calculus step, the beginning one here. So I will remind you that you have a famous trig identity back in your memory involving tan squared, and it's this one. 1 plus tan squared of x is equal to something, secant squared of x. And we're going to use this identity to just do a replacement. So I want tan squared by itself, so let's subtract 1 from both sides. So we get secant squared x, and then the whole thing subtract 1. So the original integral is equal to integral negative pi over 4 to pi over 4 of, and then instead of tan squared x, we'll just put secant squared x minus 1, the whole thing. Again, that is not calculus. We still have to do the calculus, but that is a pre-calc trig identity substitution. Okay, and then the question is, can we integrate secant squared minus 1? Well, the minus 1 is easy, right? That just becomes minus x. And the integral of secant squared on the surface appears to be no simpler than the integral of tan squared. But secant squared is actually the derivative of one of our elementary functions. Think about it for a moment. Pause the video if you don't. If you need time to think about it, because I'm just going to say the answer. Secant squared is the derivative of tangent. So that means that this is equal to the integral of secant squared x is tangent of x, not tan squared, just tan x, and then minus the integral of 1 is just x. And then this is the part where we put the whole thing in brackets, negative pi over 4 to pi over 4. And then we're going to substitute I see that I'm running out of room here. So we go tan pi over 4 minus pi over 4. That's plugging in the pi over 4 for both x's, minus, and then we'll plug in negative pi over 4 for both x's. Okay, tan pi over 4, that's 1, minus pi over 4, minus tan of negative pi over 4 is negative 1, and then that becomes a plus pi over 4 in the parentheses. And then we'll just combine like terms here. 1 minus minus 1, that's 2, minus pi over 4, subtract another pi over 4 is negative 2 pi over 4, which reduces to pi over 2. So 2 minus pi over 2. Okay, part F, integral 3x plus 8 to the 132. Okay, that 132 might seem daunting. Don't let it intimidate you. It's just the power. And if we let u equal the stuff in the parentheses, it's just going to become u to the 132, which is no problem. What is the derivative of the stuff in the parentheses? It's just plain 3. That's great because I don't have any x's I need to worry about canceling over here. So I think we've got our technique. U equal the stuff in the parentheses. du equals 3 dx. Solve for dx. Just get du over 3. So that means that the original integral is equal to integral. Instead of the parentheses, it's just u to the 132. Instead of dx, du over 3. That over 3 is a 1/3 on the outside of the integral. And then the integral of u to the 132 du. This is our basic power rule. Add 1 to the power, divide by the new power, plus c. U to the 133, now we just change the u back to 3x plus 8. So that is to the 133. Let's just multiply these two denominators, 399 plus c. G, integral from 1 to 2 of e to the 1 over x squared dx. Okay, let's see a fraction. The tendency is to let u equal the more, like the bottom, if that's more complicated. So if we let u equal x squared, the derivative is 2x. That does not at all look like what's up there. That's not going to work. Letting u equal the top, maybe, I don't know, the derivative of e to the 1 over x is e to the 1 over x times some more stuff. That's not promising because I don't have another e to the 1 over x over here to play with. So the only other thing I can think to do, because I have e to some stuff, is maybe just let u equal the stuff. So what is the derivative of 1 over x? Well, this is one of our little shortcut things. A constant over x becomes negative the constant over x squared. So the derivative of 1 over x is negative 1 over x squared. Hey, that's promising because negative 1 over x squared is basically what we have. That x squared on the bottom is really like a 1 over x squared. So I think we're good. Let's try it. So we're going to go u equals just the power, 1 over x. Du equals negative 1 over x squared dx. If you don't have that shortcut memorized, you can still find the derivative of 1 over x, either using the quotient rule if you're a glutton for punishment, or rewriting as x to the negative first, and then using the power rule. And then a little bit of rewriting gets us to this. Okay, so we'll solve this for dx, as is our technique. So we'll multiply both sides by negative x squared. So we go negative x squared du. So the original integral becomes integral 1 to 2, that might be a lie, e to the 1 over x. So that becomes e to the u. Over x squared, we're going to copy. The dx becomes what we just said. It's a negative x squared du. And then good things happen because the x squareds cancel. And so this just becomes a negative 1 up here. And now that the integral is just used, the integral from 1 to 2, those limits of integration, those are lies because these are values of x. So I think we actually need to make this change right now. So we're going to erase the 1 and the 2 in a moment. So all we need to do is figure out if x is equal to 1, how much is u, and if x is equal to 2, how much is u? And we're just going to go to our definition right here. U is 1 over x. So when x is 2, the u is just 1 over 2. And when x is 1, u is 1 over that x, so 1 over 1, or simply 1. So I think that means we need to erase top guy. So it's not 2, it's actually a half. I'll erase the bottom guy. It's kind of silly to erase the bottom guy because the bottom guy is actually still 1, but that's just sort of a coincidence in this problem. Okay, let's finish. I see a -1. I'm just going to put that on the outside. All that's left is the integral of e to the u du. That is simply e to the u. But we're not doing the plus c here. We're just integrating from 1 to a half. And literally, we are plugging into u 1 and a half. We are not going back to the 1 over x, and we're not going back to the 1 and the 2, the original limits of integration. We're good. We're not going back to x anymore. Negative, I'll just put it on the outside here. So we go e to the 1/2 minus e to the 1. And so negative e to the 1/2 plus e. It's okay to write those in the opposite order. Okay, part H. ln of x, the whole thing divided by x dx. Okay, again, first impression, should we let u equal the bottom? And gosh, that does not look promising at all. The derivative of x is just 1. That doesn't look anything like what's up there. Should we let u equal the entire numerator? So the derivative of ln of x is 1 over the stuff in the bigger parentheses, the outer parentheses, 1 over ln of x times the derivative of ln of x. But I don't see a 1 over ln of x anywhere in this, so that doesn't seem promising. But if we let u equal just the stuff in the inner parentheses, just this, then the derivative of ln of x is 1 over x, which is exactly what this x in the denominator is. So that seems promising. So just the inner ln of x, derivative is 1 over x dx. Solving for dx means multiply both sides by x. So we get x du. So that means the original integral equals integral ln of. Now the inner ln of x is what we called u. Make sure you still have the outer ln. Copy the x. Instead of dx, what we solved for, x du. Because we made a good choice for the u, good things happen with the cancellation. And now we're left with the integral of ln of u du, which is still not trivial. We actually do have a technique for integrating ln of u, and it is integration by parts. So let us use integration by parts. Okay, I'm going to erase this part in a second, but typically our integration by parts setup is this. And the v and the dv are no problem, but u and du are a problem because we've already used the letter u in this problem. So I'm actually going to change and use w. Doesn't make any difference what letter we use. When we do the integration by parts formula, we're just going to follow the same pattern, which was this times this minus the integral of that times that. Okay, so let's fill in the blanks here. So what are we going to let w equal? Well, we got to let it equal the ln of u. It's the only thing there. And then dv is just du. Coming down here, dw, the derivative of ln of u is 1 over u du. And then the integral of du is just u. And then let's go ahead and write our new integral. The original now is equal to, okay, so we're following our diagonal pattern, w times v. So that's ln of u times u minus the integral of v times dw. That's u times 1 over u du. Look, something really nice happened inside this integral. The u's just cancel. And so it's just the integral of 1. So equals ln of u times u minus, and then the integral of 1 du is just u plus c there. And then our last step is to change the u back into what we had originally, which was ln of x from way back here. So ln of x minus, times the u, but that's again ln of x, minus u, which is ln of x, plus c. That's a tough one. I, x square root of x plus 5e to the negative 5x dx. Okay, so it feels like these are really two completely separate integrals separated over this plus sign. They have nothing to do with each other. This doesn't look at all like this. So I'm going to write two separate integrals. You don't need this step, but I'll put in equals integral x squared of x. I'm going to go ahead and rewrite that as x times x to the half right now. Give this integral dx plus sign. That 5 can come outside of the new, well, I'll just leave it in for right now. 5e to the negative 5x dx. Okay, equals, all right, the first integral, x times x to the half. Let's smush them together, add the powers, x to the 3/2 dx, plus. Okay, now the second integral, I'll just copy it for right now. I'm actually not going to show the details for this one because the second one is a u substitution. And it's about as straightforward a u substitution as they come. We'll let u equal this power, and the derivative of negative 5x is negative 5, and we have positive 5 sitting right there. Write the details out, pause the video here and come back once you've got that integral worked out. But it is, really similar to this other one that I skipped over. Where'd it go? This one here. Integral of e to the 3x plus 4, ended up with a 1/3 there in front. So same deal for ours. I think all we're going to do is have a negative in the front. So let's do this first guy, x to the 3/2. Add 1 to the power, 5/2. Instead of dividing by 5/2, I'll right away flip it and make it a multiply by 2/5. Plus, but really that negative 5x over there is just going to become a negative sign. The 5 that's sitting in the front is going to cancel with a 1/5 from the u substitution, and we're just going to get e to the negative 5x, and then plus c. Okay, part J, arctan of x, integral from 0 to 1. Okay, so for this one, there's no, I think we just need to know that the inverse trig functions often yield to integration by parts. So let's try that technique for this one. U equals PV equals. Okay, we're going to let u equal the whole thing, arctan x. PV is just going to be the dx. Derivative of arctan is 1 over 1 plus x squared dx. Integral of dx is just 1x. No need for the plus c there. Let's do our integration by parts formula. U times v, arctan x times x minus the integral of v du. X times 1 over 1 plus x squared dx. I think I'm going to write up here that this is a u sub. Okay, so now we need to do this integral, x times 1 over 1 plus x squared. And this is actually another u sub. We're going to let u equal the denominator in this case, 1 plus x squared, because the derivative of that is just 2x dx. And then solving that for dx, we get du over 2x. And that's going to cancel with the x sitting in the front of this integral. So equals arctan x, I'm going to put the other times x in the front, minus integral. Copy the x, copy the 1 over, this is now a u, and then the dx becomes du over 2x. And good things happen with that u substitution because those x's cancel. And so we get x arctan x minus, okay, I'm going to do a lot here because I just don't have enough space. The integral of 1 over u du of the 2 there is just a 1/2. So I'll pull that in the front. And then the integral of 1 over u du is ln of u. And then we'll just go right back to what u was, which is arctan of x. And then don't forget the plus c at the end. Oh, but I just realized we shouldn't have a plus c on this one. We should be going between 0 and 1, because this was a definite integral. So let me add some stuff. I should have had this thing going between 0 and 1, the integral between 0 and 1, 0 to 1, 0 to 1, and then this one 0 to 1, and then actually the whole thing on the bottom line from 0 to 1. So I'll just put that like this. Okay, my space management is not happy right now, leading into like 2 problems below. We'll see how it goes. Okay, so we'll plug in 1 for every x and then 0 for every x. So plugging in 1, we get 1 arctan 1 minus half ln arctan 1. Good there. And then minus, and then when I plug in 0 for all the x's, I get 0 arctan of 0. That's nothing. Minus 1/2 ln arctan 0. Okay, and then finally, arctan of 1, looking for an angle whose tangent is equal to 1. There are infinitely many of those, but the only one that's called arctan of 1 is positive pi over 4 minus. And then I think that's all we can do here, just ln, 1/2 ln of pi over 4. It's the same arctan of 1 there. And then I think everything else vanishes because, did everything else vanish? Wait a second, ln of 0, this is a problem, gang. Okay, I have just diagnosed my error. It's crazy silly, and I'm embarrassed how long it took me to find it. But when I went back and did this u substitution right here, I said this is supposed to be ln of u, and then I quickly replaced u with arctan, looking over here. But that was not our u. That was from the integration by parts. This was our u right here. I'm sure you saw that way before I did. Sorry about that, gang. So let's fix that. Good news is math is not broken. So that goes away, and that goes away right there. This thing goes away. This thing goes away. Okay, I think we found everything here. Let's fix it. Hopefully we've erased all the bad things. Okay, so it should have been ln of 1 plus x squared. And down here, when we plug in 1 for that x, we get ln of 1 plus 1 squared, which is just ln of 2. And then when we plug in 0 for that x, we get 1 plus nothing squared, which is 1 plus 0, or 1. This makes me much happier. So this is really just pi over 4 minus 1/2 ln of 2. And then I think everything else is nothing because ln of 1 is 0. And so that's our final answer right there. Okay, part K, integral 1 over x, ln of x dx. Okay, first impressions, if I let u equal the entire denominator, then the derivative du involves the product rule, and that would be kind of complicated, and there's nothing up here that would indicate that there's promise in that root. So I don't want to let u equal the whole denominator. If I'm going to let u equal maybe just part of the denominator, I would never let u equal x, but I could maybe try letting u equal ln of x. If I do that, the derivative of ln of x is 1 over x, which is lovely because 1 over x is sitting right there. So that is our substitution. It has a lot of potential. U equals just the ln of x, not including the x in the front and not including the 1 over. Derivative is 1 over x dx. And multiply both sides by x. And we get, dx is x times du. Okay, so that means that this original integral is equal to, I've been calling it I all day, let's try it again. Integral 1 over x is there, ln of x becomes u, dx becomes x du, and then good things happen. X's cancel, and we just get the integral of 1 over u du, which is just ln of u plus c, technically with absolute value around the u. And then we go back ln of, and then instead of u, it was really ln of x. So this is ln of x plus c. Okay, part L. Integral x cosine of 2x dx. First impressions, if we let u equal cosine of 2x, then derivative is negative sign, which is not sitting anywhere out here. That's not promising. If we let u equal just the stuff inside, if we let u equal just 2x, the derivative is 2. Then I've got this extra x that isn't going to cancel with anything. That's not promising either. But what I do see here is a polynomial x multiplied by cosine of something not too complicated. And so polynomial times sine or cosine, maybe just maybe integration by parts. Let's try it. Okay, got to make a good choice here. There's only one right choice. You put the thing in u that's going to get better when you take a derivative, simpler when you take a derivative. So u is equal to x, and everything else goes on the dv side. Derivative of u is just 1 dx. That's simpler. Okay, integral of cosine of 2x. This is a full-fledged u substitution. I don't have space for the details here, but pause the video if you want and do the integral of cosine of 2x dx and then come back. But when you do the full-fledged u substitution, I think you'll get 1/2 sine of 2x plus c, but we don't write that. So again, this is a u sub with the details omitted. Okay, so now I'm ready to do my integration by parts formula right here. I equals u times v, x, 1/2 sine of 2x minus the integral of v du, 1/2 sine of 2x dx. Okay, can I squeeze this onto this line? I don't think so. Okay, the 1/2 I'll put in the front, x sine of 2x minus this 1/2 can come on the outside. Integral of sine of 2x dx, that is another u substitution. And again, I'm going to omit the details. So again, pause the video if you want to figure out the details for the integral of sine 2x dx. But ultimately, we should have another 1/2 coming outside. And then the integral of sine is negative cosine. That's going to change this to positive cosine 2x plus c. And I'm going to leave the answer just like that, although if I had a tiny bit more space to use, I would smush those 1/2s together. So in your final answer, this should become 1/4. Okay, part M, integral x minus 12 over x squared minus 4x dx. Okay, first impression, I see a denominator whose derivative maybe is sitting up here. Let's try it. If we let u equal the denominator, then du is 2x minus 4, which is sadly not just a constant multiple of x minus 12. It was worth a shot. Okay, failing that, I think we're going to take advantage of the fact that this is factorable. And if you have, polynomial over polynomial and the bottom is factorable, then there's a certain technique that I'm hoping kind of rings a bell. And the technique in this case is partial fractions. So that's what we're going to try. So let's do our setup over here. X minus 12 over x minus 4 equals, no integral, no dx, I'm just playing with the fraction. So the form for this particular partial fraction decomposition, a over x, some constant a, plus b over x minus 4. And that's going to work out because x is just a linear, single linear factor, and so is x minus 4. No repeated factors, no quadratic factors. So that's it. Lots of pre-calculus involved to find a and b. We're going to multiply both sides by x and x minus 4. Left-hand side just becomes x minus 12 equals a times x minus 4 plus b times x. Then we will pick some nice values of x to find the values of a and b. So for example, if we let x equal 4, then the left-hand side becomes negative 8, and the right-hand side, the parentheses goes to 0, and then the other part is just b times 4. So that means that b is something, negative 2. And if we let x equal 0, that will cancel out the b part. So the left-hand side becomes negative 12. Right-hand side, a times 0 minus 4. That's a times negative 4. And then plus b times 0. So I won't write that. And that tells me that a is 3. And so putting it all together, our original integral is equal to, instead of that fraction, the x minus 12 over fraction, we're going to have a over x plus b over x minus 4. So 3 over x plus, but it's a negative 2, I'll put negative 2 over x minus 4. dx, because the integrand is now more than one term, we do need parentheses here. So we'll just highlight this thing right here. Ended up going right in there after we found the values of a and b. Okay, and that integral is really just two separate integrals separated by a plus sign. I'm not going to write the details. On the first integral, it's 3 over x. That 3 is a constant multiple, comes outside. Integral of 1 over x, that's just ln of x plus. The next integral, it's the integral of negative 2 over x minus 4. That negative 2 is a constant multiplier, comes outside. So I'll change that to a minus instead of a plus. And then the integral of 1 over x minus 4 dx technically is a u substitution. You should pause the video here and write down the details if you need them for that u substitution. I'm just going to write my answer. It's ln of x minus 4. Again, absolute value, but I'll just put parentheses and then plus c. Okay, and then part n. Integral 1 over 16 minus x squared. Okay, same deal. I think maybe letting u equal the bottom, but then du is negative 2x, which is not sitting there waiting to cancel. But the bottom is factorable. So let's factor the bottom. And once we factor the bottom, I think it's going to look quite similar to the problem we just did. So this equals integral 1 over 4 minus x times 4 plus x dx. Again, partial fraction decomposition here, so we'll start with the fraction. A over 4 minus x plus b over 4 plus x. Again, non-repeated linear factors gives us just the a and the b. Okay, multiply both sides by 4 minus x, 4 plus x. So we just get 1 equals a, 4 plus x, plus b, 4 minus x. And then we'll choose some good values of x. For example, if x is negative 4, the first parentheses becomes 0. Left-hand side, technically you're plugging negative 4 for all the x's. It happens there aren't any x's, so it's 1, just plain 1. Again, the first parentheses is 0. Second parentheses becomes plus b. We just put b times, and then 4 minus negative 4 is 8. So that tells me that b is 1/8. Okay, and then letting x equal positive 4 will zero out the second parentheses. Left-hand side is always 1 in this case. A times 4 plus 4, that's 8, plus b times nothing. And so that means that a is also 1/8. Okay, so now we're ready to do our original integral. Let's do it in a different color. Here we go. So this integral now becomes integral. So it's a over 4 minus x, 1/8 over 4 minus x, plus b over 4 plus x, also 1/8 over 4 plus x, dx, again, mandatory parentheses because the integrand is more than one term. Okay, I see two separate integrals separated by that plus sign, equals here. I'm actually going to do the second integral first. It's easier. So the second integral, it's the integral of 1/8 over 4 plus x. That 1/8 is a constant multiplier for the second integral. I'll pull it outside. Now I'm just integrating 1 over 4 plus x. That is a u substitution. Pause the video here if you want to do the details. Derivative of 4 plus x is just 1, so it just becomes ln of the bottom, ln of 4 plus x. I'll put my plus c here so I don't forget it. Now the first integral is almost identical, but it's a tiny bit trickier. So the first integral 1/8 over 4 minus x. 1/8 is a constant multiplier for that integral. It comes outside. It's another u substitution, letting u equal the bottom, 4 minus x, but the derivative of 4 minus x is -1. And so there's actually going to be a -1 popping out in the front of this thing here. So I'm going to erase it, and we're just going to write our final answer. So it would have been 1/8 ln of 4 minus x, but the u substitution results in a times -1 at the end.